sklearn Gaussian process kernel's exponentiation. Description. Kernel: the kernel to be exponentiated. This could be any of the kernels provided by scikit-learn, such as the RBF kernel, the Matern kernel, or the rational quadratic kernel. Exponent: the exponent to which the kernel is raised. This value should be a positive number. Exponentiated kernel: the kernel after being raised to the specified exponent. Modified kernel output: the output of the kernel is modified based on the exponent. This modification can affect the smoothness and the scale of the output. The kernel is raised to the specified exponent element-wise. This means that each element of the kernel matrix is raised to the power of the exponent. The exponentiated kernel is then used in the Gaussian process regression or classification model. Kernel smoothness: the smoothness of the kernel can be measured by its differentiability. Higher exponents result in smoother kernels. Kernel scale: the scale of the kernel can be measured by its variance. Higher exponents result in kernels with larger variances. Kernel function plot: the kernel function for different values of the exponent. This will show how the exponent affects the shape of the kernel. Mean function plot: the mean function of the Gaussian process for different values of k. Exponent. This will show how the exponent affects the smoothness of the predictions. Exponent: adjust the exponent to control the smoothness and scale of the kernel. A higher exponent results in a smoother kernel with a larger variance. Marginal variance: the marginal variance of the Gaussian process is a measure of the uncertainty of the predictions. The marginal variance is directly proportional to the kernel's variance. Confidence intervals: the confidence intervals of the Gaussian process predictions can be calculated using the marginal variance. The width of the confidence intervals is proportional to the marginal variance. Overfitting: if the exponent is too high, the kernel can become too smooth and overfit the data. This can lead to poor generalization performance. Sample use case that resulted in challenge 1: training a Gaussian process regression model with a very high exponent on a noisy dataset. Reduce the exponent to a lower value. Underfitting: if the exponent is too low, the kernel can become too rough and underfit the data. This can lead to poor predictions, especially in regions where there is little data. Sample use case that resulted in challenge 2: training a Gaussian process classification model with a very low exponent on a dataset with complex decision boundaries. Fixes to challenge 2: increase the exponent to a higher value.